All right, so welcome back to the AP Physics 1 free response questions from 2024 AP exam. This time I'm going to be going over the three short free response questions. And then after that, I'll actually create a separate video with the two long free response questions. So let's go ahead and get started. I haven't actually taken a look at any of these yet, so I am actually going into these pretty blind. And so my hope is to kind of just go through these, right, and hopefully help you kind of see perhaps one of the more efficient ways to actually solve these. So it looks like what we have here is a block released from rest at a height of 6r, does not lose contact at any point. And question A is asking us to actually create a bar chart. It says we have the kinetic and the potential energy at point A, and we're asked to do the same thing at point B then. All right, okay, that's easy enough. So in terms of this, my guess is probably that this part is worth 2 out of the 7 points. And it should be a pretty simple one because we do know that instead of being at a height of 6r, you are actually now at a height of 2r. Since gravitational potential energy is proportional to height, then we should have 2 bars worth of potential energy, and the remaining 4 by conservation of energy should be kinetic then. So either 2 or 3 parts to this, 2 or 3 points to this. We'll kind of see what happens as we go along. All right. So starting with kinetic energy, conservation of energy, derive the expression for the speed of the block at point B. That's not too bad then, because then we still have that we have that total energy at point A has to equal total energy at point B. Right, that's conservation of energy then. In other words, work done is going to be equal to 0. I don't really know what it means by the reference book, but this is just saying conservation of energy, conservation of total energy here. All right, so we have that the gravitational potential energy at point A will have to equal gravitational potential at point B. And I apologize, my computer is actually lagging a little bit. I'll try to fix that in between the long and the short free response questions. But this kind of gives us a little bit of time to talk a little bit about these equations as I'm writing them. So we got gravitational at A, right? And then gravitational and kinetic at point B, because we're both moving and still at a height at point B then. So we have mg times 6r is going to equal mg times 2r plus 1/2 mv squared, which gives us what we're looking for then. So 1/2 mv squared. All right. And so if we wanted to solve that, right, what we're going to get is that v squared is going to equal 2 g times 4r. And then therefore the speed is going to equal square root of 8gr then. And that's our final answer for part B. So probably another 2 points for that. One for actually using conservation of energy correctly and writing that fundamental physics principle or equation, right? And then one for our correct answer there. All right, let's go ahead and move on. Okay, good. Yeah, so if I'm correct and we have, let's say, 2 points for part A, 2 points for part B, then it looks like part C would actually be 3 points, which seems about right. The free body diagram, I would say, is probably going to be worth 1 to 2 points. And then the explanation for part 2, right, the very last part of question 1 would be worth 1 point then. That would take us up to 7. All right, so it's going at point C now, and we actually have to draw our free body diagram. That's actually pretty easy. All we actually have is just normal force and gravitational force pointing downwards. So gravitational force, right, and then normal force pointing down. Student claims that for A is the minimum height so that it can slide through point C without losing contact. Briefly explain why this claim is incorrect. So let's actually go back to the diagram. It looks like point C is at a height of 4r. So what my explanation as to why the claim would be incorrect is as follows. In order to stay on in contact with the track at point C, you have to have a velocity that's greater than 0 so that k is also greater than 0. In particular, the speed should actually be equal to the square root of the radius multiplied by the acceleration due to gravity. It actually has to be greater than that uh, in order to stay in contact with the ramp. Because in that case, what you would have is you would have that m is going to equal mg is going to have to be mv squared over r rather is going to have to be greater than mg, indicating that some normal force is present. All right. And then in terms of that, right, however, conservation of energy says that all the energy at point C would be potential energy if A has a height of 4r, because then A and C would be at the same height. All right, there we go. So actually, I'm going to revise my point distribution. I think that part A is worth 2 points. Part B is also probably worth 2. Part C is probably just worth 1 point because it's actually a pretty easy free body diagram. And then part C, part 2, I would say has to be maybe 2 points then. One for talking about forces and then one for relating it to energy, perhaps. But yeah, there you go. That's problem 1. Pretty simple. So very nice. All right, let's go ahead and take a look at question 4. As I mentioned, we are actually going to skip 2 and 3 for the time being. And then we'll actually go ahead and take a look at them in our last video. All right, so it looks like question 4 is a pendulum. Yep, simple pendulum. And there's a small angle released from rest, and you have some work done. Okay, so the radius of planet X is greater than the radius of Earth, and you have to justify why the work done on planet X is going to be less than the work done. Okay, not too bad. All right, then the work done on Earth. The work done by planet X on the sphere will be less because there is a lower force of gravity acting on the sphere. I'm actually going to revise that. I'm actually just going to call it gravitational force. Force acting on the sphere. This is because planet X has a greater radius. So the gravitational field at the surface is smaller. Therefore, gravitational force and work done on the sphere are both smaller. And then in parentheses, because both spheres have the same displacement. There we go. So we talk about force and displacement to think about work done, right? And then from that, we talk about the fact that displacement is the same. You don't really have to justify why. It's kind of obvious from the situation. And then you also talk about why the force is smaller. So my guess would probably be 2 points for part A. 1 for talking about how force is smaller, right, and how that leads to a smaller work done, and then 1 for talking about why. The fact that a greater radius leads to a smaller gravitational field and therefore a gravitational force. All right, so we've got planet Y now, and let's see, same radius as Earth, but a larger mass. And we're asked to describe how Ty could be greater than Te, but how it could also be smaller than. Okay, the string is slightly elastic as well, so that's also something to consider. So greater mass for the planets would mean, before I actually get writing with my response, which I imagine is going to be our last 5 points, right? Let's kind of think about this. So greater mass for planet Y means greater gravitational field, and a greater gravitational field means a lower pendulum period. However, since the string is slightly elastic, then what you would also have is you would have that the if you increase the gravitational field, right, then you're going to increase the length of the string. And if you increase the length of the string, that is going to increase tension. And therefore, that'll increase your spring constant as well. Because if the string is stretched out, then it's going to be more tense. There's going to be a greater restoring force, or essentially a greater spring constant, perhaps. All right, I'm gonna start writing, and then we'll see if I can kind of figure out that larger part afterwards. I'm confident with the smaller part. So Ty could be smaller than Te because a larger planet mass, implies that the gravitational field is larger. Since pendulum period is since the pendulum period is inversely proportional to to gravitational field strength, which is our little g, by the way. Since that's proportional to gravitational field strength, then a larger field would mean a smaller period. Okay, I think I actually figured out what the second reason should be. However, and I'm just going to talk about it as I write. However, Ty could instead be larger than Te, because since the string is elastic, the sphere would be closer to the center of planet Y. Actually, wait, no, that doesn't work, does it? No. Yeah, sorry. Because if the sorry, Ty could be larger because since the string is elastic, the pendulum length could increase more than the gravitational field would. Since period is directly proportional to the square root of the length, right? And in addition to that, I should actually say it's inversely proportional to the square root of the gravitational field strength as well. So since period is directly proportional to square root of length, Ty could be larger than Te if the increase in length dominates over the increase in field strength. Then there we go. There's our paragraph length response. So I would say that you get 1 point for talking about each of the scenarios. So that's 2 points total. Then 2 more points for talking about how period is directly and inversely proportional, respectively, to those 2 variables. And then the fifth point for this part, 7th point overall, probably comes from just having a clear, coherent paragraph length response, as you've maybe seen in some of the international practice exam rubrics. All right, let's go ahead and take a look. This does kind of look like a momentum question for question 5. It is an elastic collision, it says, and you have to determine the speed of block B directly after the collision. This isn't too bad because what we know is that you know that block B starts at rest, and you know its final kinetic energy then. So you know that final kinetic energy has to equal initial kinetic energy plus change in kinetic energy, which is equal to 0 joules plus 9 joules. Again, we're told that it starts at rest, right? So Therefore, Kf, which is equal to 9, has to equal 1/2 mass of block B times its final speed squared, right? And so therefore you get 18 divided by 2 is equal to Vf squared, right? Or therefore Vf is going to equal 3 meters per second. All right, there we go. Before I actually move on, let's see. Okay, so this question's actually quite easy. You just got 2 more parts. So I would say that part A is probably worth 2 points, one for talking about how final kinetic energy is related to velocity, and one for getting the correct answer. All right, graph shown represents position of both of them, and you have to draw and label 3 positions. Okay, so the center of mass, because this is a collision where there's no external forces, center of mass is actually going to have a constant velocity. And we'll see if I can draw that well. So that one will be the center of mass then. So it should again have the same slope as before the collision. So I'm actually going to write that just in case that's not clear, right? It should have actually the same slope as the center of mass before the collision. So there's probably 1 point for getting that one. And then you've got block B and block A. We said that block B has a velocity of 3, so that should be the slope of block 3's line here. So block B should look something along the lines of this then, right? Block B. There you go. And then block A, we have to use conservation of momentum to actually figure out block A's final velocity. We can do that because, oh, actually, that's not going to be fun. Actually, never mind. I'm gonna actually use a little bit better way. So we know that the center of mass speed from this graph, which is given by the slope of the center of mass line here, that slope is given to be 1.5 meters per second. So therefore, what I'm going to know, one of the things that we can say is that total momentum is equal to total mass times the velocity of the center of mass for a 2-object situation. So therefore, we have MAVA after the collision, which is 6 times our unknown, plus 6 for velocity of block B times its mass is equal to total mass, which is going to be 8 times the velocity of center of mass, which is 1.5. So that gives you 12 is equal to 6 VA plus 6. So therefore, the velocity of block A after the collision has to be 1 meter per second. Okay, we're making use of the fact that in a closed system, center of mass velocity has to be constant. If you multiply center of mass velocity by total mass, you're going to end up with total momentum of the system. All right, so a slope of 1 is going to look something like that then. So there's going to be block A, sorry. 1 point for each of these lines, getting them correct with the correct slope. And then the final part C is going to be given by 2 points, right? Consider an inelastic collision, describe how the line for center of mass would change, and briefly describe your answer. The line would not change because, as we discussed, there are no external forces. And therefore, total momentum of the 2-block system is conserved. Since total momentum, there are no external forces in either situation, let's say. Since total momentum, or since P total is equal to mass total times velocity of center of mass, and both systems start with the same total momentum, VCM is the same for both types of collisions, and therefore the line, which has a slope equal to that of VCM, is also the same. So one thing, one for talking about the fact that they both systems have the same total momentum, right? And that total momentum is conserved. And then another point probably for talking about how total momentum is conserved. So 1 point for total momentum being conserved. and then relating that to center of mass velocity, actually. And there's your final 2 points. All right, so that's it for the short free response questions. Pretty quick, but thanks for watching, guys. In the next video, we'll go ahead and take a look at the 2 long free response questions.